So far we have established that using the fundamental lemma of variational calculus, we can derive an integral form for our partial differential equation. Okay, so let's try to do that. Let's consider our weighted integral form with the residual defined as e times uxx plus our uh, force function f. Okay, so then we can write our integral form defined over the domain omega as our weight function wx times rx dx is equal to 0. Now, substituting the value for our residual, we can write integration over the domain omega w of x times e times u xx plus f dx is equal to 0. Okay, and we can multiply w with each term in the bracket and write as two integral terms. Integration over omega w times e times u xx dx plus integration over the domain omega w times f dx is equal to 0. Okay, now note that the term uxx describes the second derivative of u with respect to x. So it means that for our approximation function, u tilde of x needs to be twice differentiable. And this is also known as C2. The C2 means when the function is C2, that means it's twice differentiable. C3, it's 3 times differentiable, and etc. Okay, and furthermore, the approximation function also must satisfy the prescribed boundary condition. Okay, now consider the first term of the integration here. Integration over the domain omega w times e times u xx dx. Assuming our modulus e is constant, we can then apply integration by parts and write w times u x evaluated over the boundary of the domain represented by this sign. Now this is our boundary, and this boundary in one dimensional is simply x is equal to a and x is equal to b for the domain limits. Okay, so this term minus integration over the domain omega times wx, which is the partial derivative of w with respect to x, times ux dx. Okay, this is integration by parts. Okay, now substitute this term back to our integral equation. We get times w comma x evaluated over the boundary minus integration over the domain of wx ux dx plus the first term integration over omega of w times f dx is equal to 0. Okay, now note that by using the integration by parts we have done two things. We have now the term that has the differentiation of w, our weight function, with respect to x, and we have reduced the order of differentiation for our function u. Okay. Furthermore, if you look at the boundary term, we see u comma x, which says that, which allows us to include the Neumann boundary condition in the integral form itself. Okay, so keeping these in mind, we have a couple of notes to make. The first and foremost is that this final equation is called the weak form of the partial differential equation. Okay, and why do we call this a weak form? Because it has reduced the differentiability requirement on our approximating function u tilde x. Further, our weak form requires that our weight function should be defined and bounded over the domain omega. And as you will see in your textbook, the Dirichlet boundary conditions are also known as essential boundary conditions. And to remember, these boundary conditions are defined over the primary field variables. Okay, and similarly, the Neumann boundary conditions are called natural boundary conditions. and they are defined on the secondary field variable. Okay. Keeping this in mind, the weak form is an equivalent statement of the PDE, and it satisfies all the natural boundary conditions. And you can see that over here in the term ux defined over the boundary, that it will satisfy our Neumann boundary condition, which is the natural boundary condition. Further, the weak form is valid for any weight function wx given the following. The derivative of wx exists and it is bounded over the domain omega. And w of x is equal to 0 on the boundary terms where the essential boundary conditions, which are also the Dirichlet boundary conditions, are defined.